2008 higher physics paper on questions 27 on refraction. So you're given a ray of red light with frequency 4.8 times 10 to the 14 hertz. You're given an angle. This is your angle of incidence, or your angle in glass, angle in air, sorry, and then it passes through into glass and it bends towards the normal. It bends towards the normal like we would expect it to do, so the angle of refraction is less than the angle of incidence here. The ray passes through point Y after leaving the lens. The refractive index of the glass is 1.61. There's your other piece of information there, as well as having this, and the fact that it's red light. Calculate the value of the angle theta shown in the diagram. So this is part A, part 1. So if you're looking to calculate an angle, a missing angle, the easiest way to do that is using this equation. Now the important thing about when using this equation, you can pull that straight out of the data booklet, no problem, but when you're using that, you've got to make sure that you get the right angles in the right place. So on the top of the equation, you always have the least dense material, and then on the bottom you have the more dense material. So theta 1 is your angle in air, where it is least dense, and then theta 2 is your angle in glass. You're given the refractive index of 1.61, so that tells you how much light bends, how much light changes direction. So sine theta 1 is sine 28. Just check, of course, that that angle is between the normal and the ray of light. You know, if you are given anything other than that, then you need to figure out what the angle between the ray and the normal is. So sine 28 degrees all over sine theta 2. Of course, you can write sine theta in air over sine theta in glass if you want to. That's totally fine. That's how we started off with our equation. That's what we introduced it as. But in the data booklet, it's sine theta 1 over sine theta 2. But theta 1 is 99% of the time going to be air. So solve for sine theta 2, and you'll get, in fact, solve for theta 2, and you'll get 17 degrees. So that's just simple application of that very first refraction equation that we looked at. Figure that out, 17 degrees, 2 marks for that. Next, calculate the wavelength of this light inside the lens. So this is part 2. Now there's a couple of ways you can do this. I'll do it the way that I think is easiest first. You're looking for the wavelength of the light inside the lens. So you're thinking about the extended formula and the fact that you've got sine theta 1 over sine theta 2 equals lambda 1 over lambda 2. So you don't actually know what the wavelength is outside of the glass, in other words in the air, but you can calculate it because you've got enough information to figure that out, because you're given frequency. Remember, frequency is the same outside of the glass as it is inside the glass, and you also know what speed that light is travelling at, because all light travels at 3 times 10 to the power 8 meters per second in air. So we can calculate the wavelength in air first. This is why it's a 3-mark question rather than a 2-mark, because you've basically got to perform 2 calculations. So velocity in air divided by the frequency, so that's 3 times 10 to the power 8 divided by this frequency here, 4.8 times 10 to the 14, sorry. That will give you 6.25 times 10 to the negative 7 meters. Now units aren't necessarily needed in that case, because this is an intermediate answer. It's not the final answer. This is just you getting to your final answer. And then what I would do then is use n being equal to theta 1 over theta 2. This is theta 1 that you've calculated here, because remember, all your quantities for the least dense material, usually air, go along the top. So you can use 1.61 being equal to 6.25 times 10 to the negative 7 divided by lambda 2 being the wavelength when it goes inside the glass, because remember, when something goes inside glass, it not only slows down, it not only changes direction, but its wavelength decreases. So solve for wavelength 2. It should be a value that is less than 6.25 times 10 to the negative 7, and it is. It's 3.88 times 10 to the negative 7 meters. Now that's the way that I have done that. Another way you could do it was you could calculate the velocity, the missing velocity. in other words, the velocity in glass, by using velocity in air and refractive index. That will give you 1.86 times 10 to the negative 8 meters per second. You can then use lambda equals V over F for glass, and you'll get the same answer. So that's the other way that you can do it. But that's a 3-mark question because you've got to perform those 2 different calculations here, but it's not particularly taxing as a question. B, and just for 1 mark, the ray of red light is now replaced with a ray of blue light. The ray is incident on the lens at the same point as in part A, so same angle of incidence here, but you're going to have a different angle of refraction in here because you've got a different colour of light. Through which point, X, Y or Z, will this ray pass after leaving the lens? Well, this is when you've got to go and think about the prism and how white light comes into the prism. Red light refracts not so much. Blue light refracts a good bit more. So blue light refracts a lot more, so it's going to come out at a point that's really sharper than the previous one. So it's going to go through point X, it's going to come through point X here. So you're looking to say that it goes through point X. 2 ways you could describe that. You could say blue light refracts more. Or alternatively, you could say that the refractive index of blue light is greater than the refractive index of red light. So in other words, it causes the light to bend more.